Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. A breakthrough in computational mathematics or in the supercomputer solution of a grand challenge problem is particularly worthy of being a benchmark in the history of the computer. That breakthrough is noteworthy if it changed the way we looked at the computer and the internet. With the supercomputer that communicates across processors and does so synchronously, and computes within processors and does so simultaneously, we now have answers to previously unanswerable grand challenge questions. I'm Philip Emeagwali. Calculus and algebra are the languages that I use to describe grand challenge problems arising in science and technology. Mathematics is as old as civilization. Mathematical knowledge is abstract and immutable. Where did human knowledge of mathematics come from? New mathematics came from the minds of research mathematicians working at the farthest frontiers of mathematical knowledge. New mathematics came from equations that were unseen before. New mathematics occurs when we understand how to solve the toughest problems arising in mathematics and how to solve a problem that could not be solved before. The new computing paradigm, for which I was known but not known well, was an automatically programmed and email communicated messages that I sent to and received from equidistant processors that were across the surface of a globe. In my new supercomputing paradigm that represents a new way of counting, the toughest problems arising in science and engineering and mathematics could be chopped up into 1 billion smaller problems that could be solved in a one problem to one processor corresponded manner and solved 1 billion times faster than was previously possible. My new paradigm in supercomputing was the diametrical opposite of what I learned as a 19-year-old when I began programming supercomputers back on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. In that old paradigm of large-scale computational mathematics, I programmed one isolated processor to take what seemed to be forever to solve one grand challenge problem of mathematics and physics. My contributions to mathematical physics and computational mathematics came from the bowels of my new internet that was a new global network of 65,536 processors that became a virtual supercomputer. I was asked, who invented mathematics? Mathematics is a living body of human knowledge whose pieces were invented by research mathematicians whose names were quite often lost in the mist of time. The contributions of Philip Emeagwali to mathematics is this. I contributed 9 partial differential equations to the branch of mathematics called calculus. My contributions to mathematical knowledge also includes these equations. I contributed 9 partial difference equations to the branch of mathematics called extreme scale algebra. My contributions to mathematics include this. I invented how to solve those finite difference algebraic equations and how to solve them by parallel supercomputing them across an ensemble of millions of processors. My contribution to mathematics also include this. The mathematical knowledge of how to solve the grand challenge problems arising in science and technology. Back in the 1980s, the US government publicized a list of 20 grand challenge problems of computational mathematics. Those interdisciplinary problems were at the crossroad where mathematics, science, and computer science met. Those mathematical problems were called grand challenges because no mathematician could solve any of them. I was the first computational mathematician to discover how to solve the grand challenge problems and to discover how to solve them across my new internet that is a new global network of 64 binary thousand processors that is a virtual supercomputer. What new mathematical knowledge did Philip Emeagwali contribute to mathematics? My contribution to extreme scale computational mathematics is abstract and cannot be understood by a high school math teacher. The reason is that new mathematical knowledge are discovered at the frontiers of knowledge, and to reach that frontier in turn requires 3 decades of training in the mathematical sciences. It took me 30 years from learning the times table to learning the partial differential equations of mathematical physics to arrive at the frontier of massively parallel supercomputer knowledge, where new partial differential equations of calculus and new partial difference equations of algebra can be discovered. The greatest mathematicians are famous for their contributions that increased our body of mathematical knowledge. The contribution of Philip Emeagwali to mathematics is this. I discovered how to solve the toughest problems arising in computational mathematics. Back in 1989, I was in the news headlines because I discovered how to solve such grand challenge problems and solve them across a new internet that is a new global network of 65,536 processors that were identical to each other and that shared nothing between each other. Each processor was akin to a tiny computer that operated its own operating system. My contributions to mathematics was the cover story of the May 1990 issue of Siam News. The Siam News is written by research mathematicians and written for research mathematicians. Siam is the acronym for the Society for Industrial and Applied Mathematics. Siam is a 14,000-member society of applied and computational mathematicians. My image and representations of my contributions to mathematics have been reprinted in high school mathematics textbooks and in school reports on inventors. Back on July 8, 1991, in the nation's capital, Washington, District of Columbia, I delivered an invited lecture on my contributions to mathematics. I delivered that lecture at the largest international congress of mathematicians called ICM 91. That congress is the Olympics of the world of mathematics and is held once every 4 years. The research lecture that I delivered on my new discovery of how to message pass initial boundary value problems and that I delivered at that mathematics congress was over the heads of the attendees. That research lecture was on my new parallel processed way of solving a system of partial differential equations and solving them across a new internet that is a new global network of processors. As an aside, the partial differential equations on my green board photo that was dated May 9, 1996, and that was widely reprinted as a sidebar in high school mathematics textbooks and in school reports, were formulated for multi-dimensional and multi-phase flows of crude oil, natural gas, and injected water that were flowing 1 mile deep below the surface of the earth and flowing across a production oil field that is the size of a town. The stability analysis of the numerical discretizations of those systems of partial differential equations is a grand challenge of algebra, because the direct stability analysis on the nonlinear system of partial difference equations with variable coefficients was impossible. I did what any research computational mathematician must do, namely, I investigated the theorized stability condition of a simplified version of the original initial boundary value problem. In the early 1980s, and as a research mathematician in College Park, Maryland, United States, I conducted extensive experimental stability investigations on the actual initial boundary value problem that must be parallel processed and solved to pinpoint with greater accuracy the deposits of crude oil and natural gas. From the perspective of the mathematician, climate modeling is an initial boundary value problem of calculus that must be discretized and reduced to a large-scale problem in algebra that is the discrete counterpart that is defined at finite points in space and time, and that approximated the original mathematical problem that was defined at infinite points and therefore will take forever to solve exactly. Back in the 1980s, the extreme scale computational mathematician did not know how to parallel process the extreme scale climate model and did not know how to chop that grand challenge problem into a million smaller problems, and did not know how to parallel process that ensemble of problems and do so with a one-to-one problem to processor correspondence, and do so across an ensemble of a million processors that were tightly coupled to each other. The contributions of Philip Emeagwali to mathematics is this: I discovered how to parallel process that grand challenge problem and do so across a new internet that was a new global network of 65,536 processors that were tightly coupled to each other and that shared nothing between each other. I was asked, why should the African student study mathematics? Mathematics is more than memorizing the times table of arithmetic. Mathematics is more than learning how to solve the quadratic equation of algebra. The African student must study mathematics because it's a subject that nurtures critical thinking. Critical thinking, in turn, is the most undervalued experience in education. This lack of critical thinking skill explains why a 13-year-old northern Nigerian that did not learn geometry proofs is easily convinced by Boko Haram jihadists to strap herself with a suicide bomb. To dig deeper into the quadratic equation of algebra and to be reflective of how the partial differential equation of calculus enables Nigeria to discover and recover otherwise unforeseeable crude oil and natural gas demands a significant time for reflection and thought. My passion for performing the fastest calculations began in early 1964. I was then a 9-year-old in Abo, Midwest region, Nigeria. Each late afternoon, I practiced solving 60 to 100 arithmetical problems and solving them within 60 minutes. I was practicing for the all-important 1965 Common Entrance Examination into King's College, Lagos, Nigeria. At that time, King's College was the most elite secondary school in Nigeria. The entrance examination into Nigerian secondary schools was akin to American Scholastic Aptitude Test that was at the level of a 12-year-old. That entrance examination consisted of two parts: a set of 60 questions on the English language and another set of 60 problems on arithmetic. Each problem must be solved within 60 minutes. For the 20th month onward of January 1964, and in the late afternoons, and in the evening, and in the living room of our 3-bedroom house, my father drilled me with 60 increasingly challenging arithmetic problems. I used a stop clock that stops at the 60th minute. With daily practice for the forthcoming entrance examination, the questions on mathematics became easier than those on the English language. At the All Nigeria Federal Entrance Examination, I selected the faraway all-boys boarding school, King's College, Lagos, as my first choice. I was confident that I scored 100% in the mathematics portion of that entrance examination because I had been rehearsing for that entrance examination and practicing it almost daily for nearly 2 years. I was able to finish the 60-minute test in 10 minutes. At the practice sessions, I only scored above about 90% in the English language portion of that entrance examination. So my total score of 190 was not high enough to get me an admission into the very competitive King's College, Lagos, Nigeria. My failure in 1965 to get into the most sought-after secondary school in Nigeria was a big blow to my father's ego and to mine. At age 10, my confidence in my mathematical ability was supreme. That confidence stayed with me, and I was not afraid to tackle previously unsolved mathematical problems, such as solving initial boundary value problems of mathematical physics and solving them for the first time and across a new internet that is a new global network of processors, each akin to a tiny computer that were identical to each other and that shared nothing between each other and that were tightly coupled to each other. I was confident because I was identified as very talented in mathematics and as someone that will shine in the field of mathematics. Back in early 1965, at age 10, at St. John's Primary School, Boji Abo, Midwest Region, Nigeria, my school headmaster, Mr. Okwechime, would not have been surprised if he was told that a quarter of a century later that I will be the cover story of the top mathematics publication, namely the May 1990 issue of the Science News that is published as the news journal of the Society for Industrial and Applied Mathematics. I'm Philip Emeagwali. Why must the inventor of the modern supercomputer that computes in parallel also be a research mathematician? The reason is that the research mathematician is tasked to figure out how to reduce her mathematical fiction to our physical fact. Parallel processing was first published as science fiction back on February 1, 1922. 67 years later, on July 4, 1989, that science fiction became non-fiction, and that discovery of practical parallel processing changed the way we look at the computer and the supercomputer. It's a misconception that my research in parallel processed computational mathematics was graspable to the most brilliant mathematicians in the world. Nothing could be further from the truth. To prove my point, 1.5 billion persons use or share their knowledge across 10 billion videos posted on YouTube. At least 1 million of those videos were produced as scientific lectures, with at least 1,000 of those videos delivered by the top research mathematicians in the world. Yet, you will not find any video in YouTube, other than mine, of course, in which a mathematician described the partial differential equations that he or she invented and described how he or she solved them across a new internet that is a new global network of processors. Back in 1989, it made the news headlines that an African supercomputer wizard in the United States had won the top prize in the field of supercomputing and won that prize for solving the grand challenge problem of supercomputing and for solving that problem across a new internet that is a new global network of 65,536 tightly coupled processors, and won that prize for solving the grand challenge problem of mathematical physics and for solving it at the world's fastest speed. I am that Nigerian. I am that Nigerian supercomputer scientist that was in the news back in 1989. As a supercomputer scientist, I had to quantify my parallel processed solution to the grand challenge problem as well as measure the new speeds of the physical experiments that I conducted across my new internet that was a new global network of 65,536 processors that were identical to each other and that were tightly coupled to each other and that were equal distances apart from each other. Without mathematical knowledge, supercomputing across millions of processors would be an unconstrained speculative science fiction. Mathematics is to science what paint is to art, or what words are to literature. The secret to my success as a supercomputer scientist was that my father, Nnemeka James Emeagwali, attended Christ the King College, Onitsha, Nigeria, and attended that high school for the 6 years inclusive of 1942 through 47. With that level of education, my father was able to tutor me from the times table to solving the quadratic equation of algebra. The Earth's atmosphere is a sewer for pouring carbon dioxide. Each year, 38.2 billion tons of carbon dioxide are spewed into the atmosphere. That's 5 tons, or the weight of an elephant, of carbon dioxide emissions per person per year. 62 years ago, only 9.2 billion tons of carbon dioxide were spewed into the Earth's atmosphere every year. The top 3 carbon polluting countries are China, United States, and India. If the Earth gets warmer by 2 degrees Celsius or 3.6 degrees Fahrenheit, some species will become extinct. Sea level will rise 1.5 feet by the year 2100. And some small island nations could be destroyed with hundreds of millions of refugees becoming displaced. Parallel processing is the crown jewel of extreme scale computational physics. The parallel processed solution of any grand challenge initial boundary value problem is at its mathematical core. A clarion call to solve the largest system of equations arising in algebra that in turn was derived as an approximation of a companion system of partial differential equations of calculus. 9 times out of 10. That algebraic grand challenge also underpins an extreme-scaled computational fluid dynamics code that in turn contains the basic discovery of practical parallel processing that I made on the 4th of July 1989. In his White House speech of August 26, 2000, then US President Bill Clinton described my discovery of practical parallel supercomputing as the Philip Emeagwali formula that enables computers to make fast calculations. My contributions to science stood out for one reason, namely, I worked alone. For that reason, I won the top prize in supercomputing alone and won it back in 1989 and at age 35. At that time, supercomputing was multidisciplinary. Supercomputing was a subject that drew heavily from mathematics, physics, and computer science. Therefore, it was typical for a team of 50 seasoned research scientists from different fields to cooperatively work together to solve a grand challenge initial boundary value problem of mathematical physics, such as developing the extreme scaled and the parallel processed general circulation model or the petroleum reservoir simulator. In a supercomputing research team, each scientist drew upon his or her disciplinary knowledge from his or her subspecialties within physics, mathematics, and computer science, and with the team integrating its scientific knowledge and its mathematical techniques from those sub-disciplines. Some made the egregious mistake of comparing my contributions to the development of the supercomputer that won the top prize in supercomputing and did so back in 1989 to the contributions of a team of 50 supercomputer scientists that recently won the top prize in supercomputing. It's like comparing a 50-person relay race that covered a total distance of 50 miles to a one-person race that covered the same distance of 50 miles. But more importantly, the recent contributions of the team of 50 supercomputer scientists was to reconfirm for the millionth time my primordial discovery of practical parallel supercomputing that occurred on the 4th of July 1989. Today, and in China or United States or Japan or the European Union, a multidisciplinary team of 1,000 supercomputer scientists might be given a massively parallel supercomputer that costs up to $1.25 billion. The fastest supercomputer in the world costs more than the spacecraft that took men to the moon, and costs more than the budget of each of the 40 poorest nations in the world. The fastest supercomputer in the world is knowledge intensive and for that reason cannot be within the confines of any academic institutions, in part because the fastest supercomputer costs more than the annual budget of any institution of higher education. But more importantly, the body of knowledge of parallel supercomputing is extraordinarily deep and too expansive to reside in its entirety within any single academic institution. When parallel processing meets the biggest questions in computational science, the impossible to solve becomes impossible to solve. Parallel processing is the vital technology that enables us to ask the biggest questions and then find new answers to those previously unanswered questions. I began my quest for practical parallel supercomputing in the realm of science fiction, namely by imagining the 1 binary million email wires that I must use to ingest my data and do so from outside a new internet that is a new global network of commodity off-the-shelf processors. I began that quest by imagining how to move my data efficiently and move them inside my 64 binary thousand processors that were tightly coupled to each other and that shared nothing between each other. I also imagined my email messages as sent to and received from 2 raised to power 64 processors that I imagined as encircling a globe in 64-dimensional hyperspace. I discovered that our post-human descendants of year million will find it impossible to construct their parallel supercomputer that has a 1 processor to 1 vertex correspondence with the 2 raised to power 64 vertices of the cube in 64-dimensional hyperspace. Today's grand challenge questions are more complex than ever. An example of a grand challenge problem is how to massively parallel process the extreme scale computational fluid dynamics codes that must be parallel executed when modeling the flow of blood through the human cardiovascular system. Parallel processing is an entirely new approach to modern computer science. Yet, there is a practical limit to the theoretically unlimited speed of the parallel supercomputer. Often, there is a limit to what seemed unlimited. A story about the origin of chess contains an important lesson on why the parallel supercomputer cannot be constructed with a processor to vertex correspondence with the hypercube in the 64th dimensional hyperspace. About 800 years ago, King Shiham of India loved to play games. Eventually, the king mastered and became bored with all the games known to games masters. The king invited Caesar ben Dahir, his grand vizier or prime minister, to his palace and commanded Caesar ben Dahir to invent the toughest game in the world. After a year of meditation and hard work, the Grand Vizier returned to the palace. "Have you invented the toughest game in the world?" the king asked his Grand Vizier. "Yes," the Grand Vizier answered. "I call it Chaturanga." That new game, Chaturanga, is the precursor of the modern chess, a game that beckons upon the most intelligent persons. Chaturanga is played on a game board that is comprised of 8 rows and 8 columns, or 64 black and white checkered squares. After playing Chaturanga, the king explained, "This is the toughest game in the world. Name your reward for this invention." The Grand Vizier thought carefully and then said, My reward for inventing chaturanga is a pile of rice. Why don't you ask for gold instead of rice? The king wondered aloud. Gesturing to the 64 squares on his new chessboard, chaturanga, the Grand Vizier asked for a grain of rice for the first square, 2 grains for the second, and 4 grains for the third. The king thought this was a silly request. Is that all? 7 grains? The king interrupted the Grand Vizier. No, the Grand Vizier continued. Each square got double what the last square got. All 64 squares get their grains of rice. Puzzled, the king protested. I have a greater reward. Take my daughter's hand in marriage. Your Majesty, the Vizier said, I'm a happily married man. Oh, how can I forget Mrs. Vizier? The king commanded his aides to bring a spoonful of rice and fill all 64 squares of the new chessboard, with each square allocated double what the previous square got. The servant started counting the grains of rice, 1, 2, 4, and soon the first teaspoonful of rice was used up. Then 4 bags of rice were required. Then the king got pale as 1,024 bags of rice, then 1 binary million bags of rice were gone at the 20th square. The amount of rice needed seemed infinite. The total grains of rice needed for all 64 squares was 2 raised to power 64 minus 1, or 18 quintillion grains of rice, or about 18, followed by 18 zeros, grains of rice. The total bags of rice the Grand Vizier demanded was equal to the total amount of rice that was ever harvested by all the rice farmers that had ever lived on planet Earth. That amount of rice will cover the earth many times over and has the mass of Mount Everest. I share this story from the 13th century India and did so to highlight the invincible limits to the speed of the future planetary-sized supercomputer. But I also use this story to explain to children why it's impossible to scrub off a picture that's gone viral on the internet. You share your picture with 2 Facebook friends, then share it with 4 friends, and when your picture has gone viral, you cannot scrub it out of the internet. I also share this story because I once speculated that supercomputer scientists of the 22nd century or further could parallel process across their internet that could be defined and outlined by 2 raised to power 64 commodity processors that had a 1-to-1 processor to vertex correspondence and had that relationship with the vertices of a cube that is tightly circumscribed by a globe in the 64th dimensional hyperspace. I'm Philip Emeagwali. I'm known as the first massively parallel supercomputer scientist and as the first person to discover how 1 million processors can be fused together by as many email messages and fused together to form one whole cohesive unit that is a new computing machinery that is the world's fastest computer that made the news headlines back in 1989. The new supercomputer, that is a new internet that I invented on July 4, 1989, is radically different from the constituent processors that it originated from. As an aside, and in my dictionary, the words computer and internet are like two sides of the same coin. I believe that the 22nd century supercomputer scientists cannot have an internet that is not also a parallel supercomputer, or vice versa. The moral of my story of the origin of chess in the 13th century India and its lesson for the planetary-sized supercomputer hopeful of the 22nd century was that at the beginning I was as unaware as the king, but at the end I became as knowledgeable as the Grand Vizier. At first, and back in early 1980s, I grossly underestimated the power of Dublin. I once thought that I could simultaneously program to raise to power 64 number of processors and synchronously send and receive email messages across a new internet that I visualized as a new global network of 64 times 2 raised to power 64 number of bidirectional email wires. A third important lesson of my story of the origin of chess in the 13th century India lies in the uncontrolled growth of the population of Nigeria, my country of birth. Nigeria is now the 7th most populous nation in the world. Nigeria is a little bigger than Texas, but could grow by mid-21st century to become the 3rd most populous nation in the world. Last year, Nigeria welcomed 5.5 million newborns, or 40% more babies than the United States. This year, Nigeria will welcome more than the population of Libya, or Norway, or New Zealand. The planetary-sized vision that inspired my contribution to the development of the supercomputer is this. The Earth is enshrouded by fluids, namely the atmosphere and the oceans, as well as the rivers and lakes, and also surrounded by subterranean fluids, such as crude oil, natural gas, and water. To invent a new internet that is a new supercomputer de facto, I visualized 65,536 processors as equal distances apart and within the fluids that enshroud the Earth. I envisioned a globe in the 16th dimension that was encircled by 2 raised to power 16, or 65,536 commodity off-the-shelf processors that were distributed equal distances apart from each other and that were tightly coupled to each other and that shared nothing between each other. I envisioned each processor as having its own operating system. I envisioned those 64 binary thousand processors as embedded within the fluid or atmospheres and oceans that enshroud the Earth or globe. I envisioned that globe as tightly encircling a cube with 16 times 2 raised to power 16, or 1,048,576 bidirectional edges. In the modern configuration of supercomputers, and at 1 foot per email wire, those email wires will total 200 miles of cables. Each vertex on the surface of that globe was my metaphor for one processor. Each bidirectional edge on the surface of that globe was my metaphor for one email wire. That globe is my metaphor for the Earth. That new global network of 64 binary thousand processors is one of the two internets that I invented as two supercomputers and is the reason I was profiled in books, such as the one titled History of the Internet. I envisioned each processor as simulating the motions of the nearest 3,000 square miles of fluids. I invented a new supercomputer that encircled the globe in the way the internet does, and that could be used to solve never before solved problems in algebra. I invented two new supercomputers. My first supercomputer was constructively reduced to practice as an ensemble of processors that encircle the globe in the way the internet does. My second supercomputer was an actual reduction to practice of 65,536 processors that encircled the globe in the 16th dimension and did so in the way the internet does. That parallel supercomputer became super by computing faster than any scalar or vector supercomputer. That new supercomputer enables the computational mathematician and physicist to answer previously unanswerable questions arising in extreme scale algebra. Such questions are recurring decimals in the grand challenge problems of supercomputing. By definition, algebra is the generalization of arithmetic. In high school algebra, two letters represent two numbers. In the supercomputer algebra that arises from trying to discover and recover otherwise elusive crude oil and natural gas, 1 trillion letters must represent 1 trillion numbers arising from a system of 1 trillion equations of algebra. Those 1 trillion equations are evenly distributed across 1 million processors that in turn solves them in parallel by computing 1 million calculations at once. Thank you. I'm Philip Emeagwali. Thank you very much.
Insightful and brilliant lecture. Insightful and brilliant lecture.